So let me maybe state what we proved last time. So the kind of the setup we're currently in is we have some expansion of the real field. And essentially, if I forget saying this, currently essentially we want to look at what we sometimes call the type A case, but this really means that this structure for in this case here is equivalent to saying that this does not define. And what we proved last time was this what we called the strong bare category theorem. Category, and this really just said that if you have, say, let's say notation says E, this is the sigma. So the sigma was this kind of increasing union of close defined sets. Then E either has exterior, oh no, there's no way. So even if I repeat myself, this is kind of a strong version of the usual bare category theorem. The usual bare category theorem, you would have every sigma here, so it's a countable union of compact sets. And as we have argued before, D sigma implies F sigma, but it's, not the other way around. And in this case, you only get this kind of, instead of nowhere dense, this traditional Poincaré, you would only get meager, which is somehow a countable union of nowhere dense sets. But that again, a meager set can be dense. So the difference here is really this kind of so that you get nowhere denseness. And so what I want to do today is essentially just get all the corollaries. And so it's really, I mean, so I want to get corollaries of it, and they're very much in the spirit of o-minimality as well. This is really some kind of, looks more like, I mean, some kind of strengthening of the descriptive set theory. I hope to give, after this lecture, you might have the impression that this is really something geometric. Okay, so let me move this up. And for that, I need to define a couple of things. So essentially what I want to talk about in the following is continuity and then monotonicity and so on. And for that, I need to fix a few definitions from really basic analysis. So now no mentioning of definability for a second, so that X be a subset of R to the N. And when we want to talk about continuity, we do this by talking first about oscillation at a point, so that F be any function from this X, whatever it is, to R to the different M, and you take an epsilon in larger than 0, then we say F is oscillation at some point at X in X, if, well, for all epsilon larger than 0, there are y, let's say y prime in X, such that the distance from both X and X prime, whatever this precise norm is, doesn't matter too much, whichever you chose, the infinity norm, that's fine. So if they are both the distance between y prime and y from X is small, but the distance from between some X between these two is that's what I read. Okay. So, and then what the fact we want to use, I mean, you can imagine that if you want to talk about the sigma sets and we want to have somehow closed sets, and what we have is say set the set of all these, check the set of x and x, at which f has oscillation epsilon. Epsilon is post, we say index. Okay. Okay, and so then what would, of course, at the point of this overview, then the set of points at which you have the union of all these points where you have oscillations, of course, a point of discontinuity. So we have that, and then this is still the same assumption. F is discontinuous at x if F has epsilon oscillation some and so, for example, if x is out to the n, what this then gives you is that if x is say out to the n, f is a definable function, then what this really just means is that the point of discontinuity of f is a sigma set, because of course this gives you the set of points where the f oscillator with epsilon gives you an increasing family, and this is really what we're now going to do. So let me make this a proper lemma. So lemma 4.2 now says that again, as I tell you, why take open subset and definable. Now you take a definable function, say u r to the n and be definable. Then I have two statements. The first statement is, this is kind of that we really don't need any kind of assumption on the expansion, or we don't need something saying that the expansion doesn't define the integers. This is really just almost immediate a set of points at which x at f is discontinuous. Continuous rotation from x is sigma. So that we need nothing. That's just from the facts from real analysis. But of course, what now we want to apply the strong back category theorem. So if you know that it's the sigma, then what this will give us that either it's either interior or it's nowhere dense. And so that gives us then can tell us a little bit more. So the set of point at which is discontinuous and one of the following points. This will essentially say that either we're in the case that the point of discontinuity are interior or we're not. And so the first case is that we are not. So there is an open definable set V subset of the U we started with, such that the restriction restricted to B is continuous. Okay. Or, and this is not a kind of or if it's not, so if this does not hold, then there is an open interval, well, there's an epsilon and an open definable set U and epsilon larger than 0, such that F has epsilon oscillation for every exit. I'll give you a quick proof of that in just a moment. I mean, I want to give you an example. I think it's kind of so you might say, okay, really, can we prove that 2 doesn't hold? Should somehow Tameness give you that 2 doesn't possibly be true, so that you always get a continuity on open definable subset? Well, see, the problem is that, and we talked about this earlier on, that you take the real field and you expand it by the real algebraics. This was this kind of, we had this before, this was this having o-minimal open core. So this is rather well behaved. And then take the characteristic function of the rationals, or the sort of the real algebraics, sorry. And this is really, this says oscillation 1. It's nothing. Sure, okay. So again, so if you just take any definable function, then this is the best thing you can do. We still don't know, and I mean that could be then really true. Is we talk so much about Miller's conjecture. If Miller's conjecture hold, I could imagine that then if F is definable in the open core of R, that this then would be true without the second. But that we don't know. So let me give you here the proof of this. So prove that epsilon be larger than 0 and set a epsilon be the points are not, I will give that name, be the points oscillation epsilon, and then you see that set A0 would be the union of all of this, and so this is the point of discontinuity. That A epsilon be the point of the oscillation epsilon as defined, and then if you take the union, of course you get the point of discontinuity. You have to be a little bit careful. I think the so this is closed in. We only said that this is closed in U. So it's so you have to what I leave as an excess. You have to show, and this follows from what we had, that each A epsilon is the sigma closed, right? And so then we had this kind of what was it? I think it was 341 or 314 that said that if you have an increasing union of the sigma sets, then the union is the sigma again. So then by A0. So now we can apply the category theorem, the strong Baer category theorem. So we either get that A0 has interior or it's nowhere dense. If right now strong Baer category theorem implies that A0 has either interior or is nowhere dense. So if it has interior, no, so if it's nowhere dense, sorry, so if it's nowhere dense, and the point of discontinuity at nowhere dense, so the complement of that nowhere dense set, of course, then has interior and in U, and that's the point of discontinuity. So if it has is nowhere dense, then we're in situation 1 and we're done. So is nowhere dense. So now the last thing. So if nowhere dense, now we just have the interior case. So suppose A0 has interior, and then by the okay, then if one of the suppose none of the no A epsilon has interior, well, if one of them would have it, then we would be done, because otherwise 2 would be true. This one of, remember that A epsilon is a set of where F has oscillation of least epsilon. So if this would, if A epsilon would have interior, you would have this kind of set where you have the interior and where you have this oscillation on an interval, an open set, and this was precisely what say 2 said. So then we know A epsilon has interior, so again by the Baire category theorem, by the strong Baire category theorem, this implies that all are nowhere dense, and okay, now you can, if you want, you can take just the standard Baire category theorem. If you have a union, make this a countable union of nowhere dense sets that cannot have interior. So this means that A, which is the union of the A epsilons, has no interior. So that's a contradiction. Okay, so we have now that if we have a definable function in this expansion that does not define the integers, then either it's essentially interior, you have a dense open set where it's continuous, or this is now the second case, you have a full interval in which you have oscillation. Okay, so now let me give you here one of the examples of this application. So let me introduce one more notation from the set theory, and I think that's a kind of my preferred way of applying this. And maybe I should say this here at this point, that's a good place to start this. So often in this kind of talk, I use this kind of results that only hold, over the reals in some sense. For example, just a moment ago, I actually used the traditional Baire category theorem. In almost all cases, I think in all cases in this talk, I'll use this for convenience. There's kind of, if you want to work in a more general setting, you can. But for this talk, I really don't want to. I'm happy to work just a bit. Okay, and one of these examples now follows 2. So one of the notions I want to define, I would have to be a bit careful if you don't work over the reals, but if you do, that's fine. So what I just want to introduce, in case you've never seen this before, is what's called the Baire class 1 function. And the Baire class 1 function is essentially just a, say f is Baire class 1. Well, if it is the union, the pointwise limit of a family, it is the pointwise limit. Sequence. continuous functions with domain okay. So why do I mention that plus one? Because over on the reals we know that the points of discontinuity of such bare class 1 functions are small in the kind of descriptive set theory sense. So if you combine, so if you know that you have f, and I will do this in the next step, if you have f and it's bare class 1, you know the points of discontinuity have to be small. If you know that's a definable bare class 1 function in the expansion of the real field that doesn't define the integer, but those points have to be really small, or the set has to be really small. So you get essentially that bare class 1 function are the continuous outside an overhead set. So now let me this. I was trying to see whether I could go through the whole hour with just using the 9 boards, but it seems like that. So this is now 4.4. So now this is now the descriptive set, or for this maybe I use this descriptive set result in the proof of this result. So let this be open. Let again from U to R now definable. And we assume that we work in this type A or Tame integer structure, be definable and bare class 1. Then f is continuous. Continuous on open dense subset so dense subset. So really the proof here is as I already said, by the descriptive set theory. I mean, this is a descriptive set theory saying that sounds like this is something recent. It's a classical result in real analysis, is that there's kind of points of discontinuity. German, I can say the study of f are co-meager. Of continuous, one of them. So the points of discontinuity are meager. So the points of continuity are co-meager. So that means by what is it, 4.2? That's really what we showed. After the open dense. Okay. After points of continuity. Now I've turned it around. So this means there have to be nowhere dense. Because if there would be somewhere dense, there would have to have it too. Okay. Now I have one more. So this looks not. I mean, this is actually crucial for many things. And the main, maybe I make this an observation. So if you have never thought about bare class 1 functions, the class which I care the most about among these bare class 1 functions that seem lower semi-continuous functions. Lower semi-continuous or bare class 1. Yes. Lower semi-continuous, if you again, I'm fine. is that if you lower semi-continuous and then point x0, if the limit lim of f of x, if you go to this point x0, is smaller or equal to f of x. That's a limit. So I leave this as next. I mean, it's kind of not trivial, but you can check that lower semi-continuous functions are back possible. Well, check the Wikipedia article, it's proven there. So what is, I just want to draw one picture, because I think this is what I say in the next fact, which again is a fact from real analysis that I don't want to prove. Is, I mean, really what this the picture that you always see is something like this. So if you might have this kind of point of discontinuity there, and if you want it to be lower semi-continuous, then you have to have this point has to be here and not here. That's really what. So then, for the intents of purpose of this course, what limit lower semi-continuous is.
X0 then, right?
Yes, so x0. Yes. X0. Thank you. Okay. Okay, so now where do their lower semi-continuous functions appear? They're called one functions. Is just compact here, so it's now 4.5. So now I want to give you the example where in this kind of whole business of Tameness these functions appear, so that A be a subset of R to the M, let's do +1, closed, and let U be a non-empty open set the subset of the projection of P of A. So P of P is pi is right. So just a projection from R to the n plus 1 onto the first m coordinates. And so now what you can do, and this is where now the this kind of what is lower semi-continuous, you can of course, if you are in the projection, if you are in this pi of A, so if you're in this U, you can always take the minimal element in the fiber over A. That's a function, right? So then and it's of course also redefinable. So then the function so far I don't say anything about definable, so this function you can always define. But the point is that if you have A over the real field, then this function that I'm now going to define will be definable as well. You don't even need the field that maps P in U to the minimum because it's closed, you have a minimum of AP where A is the field. Ah, okay.
I mean,
yeah.
So you do. Otherwise, it gets annoying. Right? It's all of ours. It's 2 hours.
Yes. Okay. I would be happy. I think for the application, I would be happy to also restrict simply to that all the APs lie in the positive or that are larger or equal to 0. That would be interesting.
So then the function f that maps this to this.
Yeah. Okay.
No, what I'm saying is what are we saying about f?
Also, yes, thank you. Almost getting it's lower semi-continuous. And I mean, I made this comment here in brackets, definable if A is. So in particular, so now if you're under the assumption on the that we don't define the integers and we have what is it now, 4.4. So by 4.4, if f is definable, A is definable, then f is continuous outside and nowhere that's set. So we'll move this up. Always wait a moment. For me, this is the absolutely crucial result. I mean, for me, this is if you want to say anything about in this kind of expansion, in this generality about sets living in R to the n, or even just R2, this is what you need. Let me draw a picture for you to see that why this is the kind of thing. So in the kind of, and then on Friday I'll put a few things about just work in the line, but if you want to extend any kind of result to higher hierarchy or have some form of cell decomposition maybe at some point, then you really need to do that. And the reason is that, I mean, really what this really tells you, try to draw a picture here. Of course, with drawing these kind of pictures is that if you draw pictures about o-minimal structures, then I think more or less when you draw it, you actually give a good expression of what can actually happen. Of course, here they kind of all kind of very small, very fractal objects, and that is very hard to draw. So what I want to have here is maybe in green. You have some set A here. Maybe I want to make this here a little bit, so maybe have some kind of. So and really, what you don't have is. So this was our set A. This was our with the closed set. In this case, even compact. And then let's say here, this is your U. And then really what this says is that after you throw away some of this kind of nowhere dense set, in this case, really, I think it's really this kind of point, then what you have that outside this nowhere dense set is the minimum thing that you have in the set A really looks like a continuous function. And so what you do have is that outside a nowhere dense set, you really have this kind of nice control. Of course, if you really want to make this kind of picture more sensible, nowhere dense set is much bigger than the single point. So this is, I mean, really just a character. You could have many of these points here. And we would have another point of discontinuity here. Another one, but so there's still, I mean, you have this kind of what we consider a small set, and you throw this out, and then above that, this really looks like what you would hope. But of course, again, I said this before. This is and if you look at this, is probably a set definable in an o-minimal structure. So then this will look much more complicated down here. It's kind of all things you might have in here or even here will look more in most generality much more complicated. But this kind of result is kind of showing that we can have some hopes of getting something which is so far we really know just for the line that this kind of moves. Okay. Good. So I will come back to this higher dimensional questions Friday.
Isn't Philipp,
Yes, please.
maybe that this inequality theory was the wrong way around.
That's right. And right.
It's not clear what that picture is. But,
That is an example of lower semi-continuous function.
right, I thought you were also saying that the dot had somewhere on there.
I guess doesn't matter. We're
Right.
using a direction in which X is approaching it.
Oh, I see. No, okay, I draw this picture. No, sorry, that's right. The kind of in this picture here, the dot would always be down here.
No, it's just do one where it draw where have it come in and then one down below is an example that it's not. That's good.
So just to clarify, so
Yes, please.
if we moved it, so here we have f of x 0, and we have f is approaching two different values, one from the left, one from the right. And we've set the value at x 0 to the lower one.
Yes.
Are you trying to say that if we set that value to the higher one, then the function would no longer be lower semi-continuous?
Would be that upper semi.
No, it's final. Still be close.
By the inequality that you've given it. would be-
Oh, I see. Yeah.
Yeah.
I see. Yes. Okay. Okay, let me not try to do this in color 4 without looking it up.
So you're trying to give an example. The point is, were you trying to give an example of one or a counterexample of one?
I want to give an example.
Okay, that's definitely more simple.
Yes. No, I mean, I wanted to give I wanted to give an example of one where this kind of this kind of points of discontinuity, the same thing happens. As in the case of the say taking this minimum over when you have a complex set.
Yeah, but in this one, the value of that could be either. Could be either.
I just looked up lower semi-continuity on Wikipedia, and they have this exact inequality except flip the other way around.
Right.
They say greater than or equal to. Sorry.
Okay. Okay. So next time I just show the Wikipedia thing and don't try to copy paste this. Okay, so about the time, yes, I just not the proof, but I want to state here. So, and this is so the idea of o-minimality is really that you get here some form of monotonicity. And this is again, I've stated something here, and again, this should not be considered kind of the last page of the story or the kind of the end of the story, but I think this could be restricted to something strong can be true. So let F be now the subset as a function from U to R, U be open, F definable, and continuous. It's currently, so of course, as you know, in the monotonicity structure, there's no assumption on continuity. You really just prove non-continuity. So here you have to assume something, because really, as I said, take the characteristic. I mean, still, just the camera is this kind of characteristic function. Of course, I mean this doesn't satisfy any kind of continuity. As I said, any kind of monotonicity. So then what you get there is, nowhere tends release such a subset U such that F, such that, let's get the quantification right, such that every connected component complement F is either Now the same as in your minimal setting, but strictly increasing, strictly decreasing, or so again, so I say this one more time here. I said you have the assumption of continuity. So if Miller's conjecture is true, I would also hope that this continuity could be replaced by definable and open core. And then I think this would be that would be, I think, striking, because then you would have a real monotonicity theorem for arbitrary extension. But again, this kind of there's a limit, as I said. You cannot hope this to be true without some kind of assumption. And now is I think I will get time, yeah, do the proof, or at least state how you're going to do it. And the point is really, I think Chris pointed this out in this paper 20 years ago. It's really that many of these arguments that work for minimal structures really do work in some kind of much more generality. The kind of o-minimality often comes in is where you somewhat start assuming that you want the nowhere dense set to be finite. Many of the arguments really don't. For many of the arguments that the o-minimality as such is not so crucial. And the same thing here. So if you assume that this works really the same way for o-minimality, so what you easily. So what you do is you define these three sets. So you take the sets where f is which one do I want first? Constant on an interval x, and E2 it's the same thing but strictly increasing around an interval x, and then E3 strictly decreasing. All the rest stays the same. So now what you should observe is that, so now you said each vi is open, and then you check this check. F on the connected components of the VIs, the connected components of the I, the conclusion holds. So on so F is either constant, strictly increasing, strictly decreasing on the connected components of the I. Constant if you're in V1, strictly decreasing if you're in V2. Okay, so the last thing you really have to show is that the complement of the union of the V1 to V3 in U is doesn't have interior. So left to show U minus the union has no interior. Okay. Look with that one. So suppose not. So let I be compact, be an interval in this complement. So then F. So now since F restriction to this complement is continuous, because we assume that F is continuous. So I think if you do the argument in the o-minimal case, you would there you would use the fact that you can prove that functions of the o-minimal structure are continuous outside the finite set and non-constant, because I is not contained in V1. So that then gives us so that then means that then Fi contains an open interval. And so here we use the intermediate value theorem. So we work here over the real, so we do have this around. And so then now what we do is we define, this is in the kind of the normal case, we define the inverse. So define G, now going the other way around from J to R, such a GR, GX is mapped to the minimum. Here's now where we apply the previous result pretty correctly. Minimum of the inverse image. So this is a set, because there might be many of the points things mapping to X. So you take all the inverse images and you intersect it with I. Note that this is kind of still no use of anything. Note that G is injective. However, now we have to apply our done. Now we have to kind of apply what we have before, because we now have that this kind of G is precisely of this form picking a minimal element in a closed set. Because F is continuous, the inverse image of a point is hopefully something closed. So by 4.5, there is an open interval on which this G is continuous. Open interval J prime subset of J, such that G is continuous, F is continuous, and so this means that G is homeomorphism, so maps J prime subset of J homeomorphically onto an open subinterval I prime of I. And if you have something like this is again general factor analysis, this will be strictly monotone. As the inverse here is strictly monotone. Increasing or decreasing, but in any case, this gives you a contradiction because we assume because we assumed that on this V1 to V2, V1 in the union of V1 to V2 to V3, that in the complement of those, I'm sorry, that I'm going to say it again, that I prime is in the complement of the union of the V1 to V3. So that's it. And this is more or less a minor adaptation of what Chris had in his paper on Tameness a long time ago, and he proved it there really just under the assumption that you know that every set is either has interior nowhere dense, but it works in this kind of generality. But with the assumption of continuity.
Okay, right, that's it for today. Next time I'll talk about geometric geometry, and I will talk about how this then possibly could go up into higher dimensions.